Welcome to lesson 3 of industrial automation and control. In this lesson, which is entitled energy savings with variable speed drives, we are going to explain and demonstrate that for a kind of application which is very predominant in the industry, very common, how what are the firstly we are going to see what are the various kinds of flow control applications, that is the application that we are trying to consider. So, flow can be of gas or liquid. So, accordingly we have either what are known as fans or blowers, or we have pumps. Fans, blowers and pumps constitute an enormous a very significant fraction of the loads which are driven by motors, and motors which consume a large amount of electrical power in the industry. So, they are very common applications and very significant from the energy point of view. So, we are going to see that in such applications how flow is to be controlled, and then we are also going to see that if you flow is typically controlled by driving a pump by a motor, but if you drive a pump by a motor, then it will drive a certain amount of air, let us say. If you have a pump, it could be water. Now, the demand for this air or water is not the same all the time. So, the flow has to be controlled. Now, there are so firstly, how do we, when we connect a machine to the pump, what is the amount of flow that is established? That depends on the pump characteristics, that depends on the machine characteristics. So, we are going to see that how when you connect a pump or a fan with a so called load, how is the operating point established, what will be the pressure, what will be the flow. It is actually much like establishing an operating point when you connect a battery with a circuit or a load, right. So, we are going to see that, and we will see that depending on how we can vary this operating point. See, we have to vary this operating point because we need to vary the flow. Now, the flow can be varied by various ways of varying the operating point, and it is so some of these ways are maybe very simple, but may not be efficient from an energy point of view, while others may involve more complex technology, but possibly would be more energy saving. So, we are going to look at two of the most common techniques and show that how their energy characteristics are going to be different. In fact, that will motivate the next few lessons in this course that we are going to have on industrial drives. Probably this lesson would show why industrial drives are show at least one side of the story, that why variable speed drives are such an important thing, such an important technology in industrial automation and control. So, finally, we would also see in this in the course of discussion that when to choose what type of flow control or drive, right. It is not that you always energy saving is the all important criterion. So, we will discuss a little bit on that. So, let us look at a basic characteristic of a fan, right. So, here we are, the fan is this is the intrinsic characteristic of the fan itself, irrespective of what the load is. So, the fan actually develops a pressure at its outlet and also develops a certain flow, and this it develops when the fan is rotated at a certain speed. So, when we have plotted this curve, which is whose one axis is flow and the other axis is pressure. So, it shows the pressure is somewhat like voltage and flow is somewhat like current. So, in that sense it is like, since we are many of us are electrical engineers. So, this is somewhat like a VI characteristics of a battery or an energy source. And we must remember that this curve is drawn at some speed, at a given speed. Of rotation. So, if the speed of rotation is changed, then this characteristic will shift up and down. Actually, you will get a family of characteristics with decreasing speed, right. So, this is the characteristics of the fan as such. Now, if this fan is now connected to a load, right, the load means that it could be various things. For example, typically fans are used in furnaces. So, in the furnace, typically if you go to a power station, you will find that you have big boilers, and these boilers are heated by furnaces, and these furnaces have two huge fans. One is called an induced draft fan, another is called a forced draft fan. So, these are like, I mean, a furnace is like a chula. So, you need to blow water, air into it for combustion. So, these fans actually blow that air, and the induced draft fan actually sucks out the after combustion air, most full of carbon dioxide. So, these are so it is the furnace which is the load. So, if you connect the fan to the furnace, then at a certain speed of the fan, a certain operating point or a certain pressure flow will be established. So, basically how do we get that? So, this is a fan characteristics which will come back to a little later. This is a little complicated. Actually, basically, okay, let us have a look at it. Basically, what is being done is that this actually gives a family of curves, right. So, on this axis you have this CFM, means cubic feet, which is an unit of volume per minute. So, this is nothing but volume flow rate. So, this axis is Q, right, and this is total pressure in inches of water column, right. So, basically this is pressure or P. Now, so you see part of the fan characteristic is shown, and you can see that a family of curves are shown. So, what are these family of curves? So, basically the various operating points, for example, these are, if you see these constant lines, I will draw it here. So, for example, this line, it starts with this number 500, and here it is written RPM. So, which means that this is the, if the fan is made to rotate at 500 RPM, then the pressure flow characteristic follows this curve. Similarly, you have a family of curves for various speeds. On the other hand, look at these dotted lines. So, this dotted line, it says 150. So, these are constant horsepower lines. So, these are constant horsepower lines. So, if you operate it along this curve, then you always spend 150 horsepower. Similarly, you have a number of curves, right. Similarly, you can have efficiency, constant efficiency characteristics. Say this is 70% line, this is the 80% line and so on. So, basically this curve shows that if the fan is operated at various speeds, what are going to, so basically pressure flow characteristics with something constant, either the speed is constant or the energy is constant. So, so that you can conveniently find operating points, and in fact we will use this curve later on to find out, to actually compute the energy savings, right. So, having understood this, let us move on, and we will come back to this curve in a while. Yes. So, here now we come back to how an operating point is established. So, you see, just like remember that when we computed operating points in our circuits courses, we drew what is known as a load line, right. So, on the other hand, you have a load has a certain characteristic, means that if you want to create a certain amount of flow through that load, in this case maybe through the furnace, you need to create a certain amount of pressure difference, right. Suppose you take a pipe, then to be able to create a certain amount of flow through the pipe, you need to create a certain amount of pressure difference across the two ends of the pipe. So, that is the characteristic of the pipe, that to create a given amount of flow, how much pressure difference is needed, and typically it turns out that it follows a square law. Basically that occurs because of Bernoulli flows when you have what is known as turbulent flow. That means when the flow velocity is high, then there is a law called Bernoulli's law, which we are not going to now, from which you can derive that the pressure flow relationships through any constriction, if the flow velocity is sufficiently high, that is if the Reynolds number is so high that the flow can be called turbulent, then typically the pressure flow relationship is quadratic. So, the load typically follows such an equation with some constant k. So, if it is a narrow constriction, this value of k is going to be high. If it is a open constriction, value of k is going to be low, and so on. So, if you connect such a load across the pump, then they will intersect, and this is the operating point. So, this is the operating point. So, immediately if you connect, this is the flow and this is the pressure which are going to be established. So, the pressure which will be established, if you connect this pump with this load, this flow will be established and this pressure will be established, right. So, now let us talk about varying the flow, because we need to, depending on the load characteristics. For example, if your electrical energy demand decreases, then you need to reduce the rate of combustion. So, you need to reduce the flow, air flow into the furnace, right. So, how do you do that? So, typically it happens, this is a typical case. We are calling it a system load profile, which means that the system to which we have connected the load, what do you mean by the load? We mean by the load we mean flow rate. So, you see that this is the demand, a typical demand profile. So, it says that this is, let us say that this is the maximum flow is 100, that can occur, that we are calling 100%. So, since we must have kept some amount of safety margin, so probably maximum flow hardly ever occurs, maybe it does not occur at all, or maybe occurs for a very small time. So, most of the time, that is, the flow is actually between, you see, about 45 to 70%. So, this maximum time the flow stays within 45 to 70% of the design flow range. Similarly, it stays at it stays between 40 and 45% for, so that is about 11 point something this percent of the time. So, 1, 2, 3, 4, 5, so about more than 50% of the time it stays within this flow range, and similarly it stays within 25 to 30% for 1% of time and 30 to 35% about 4% of time, and so on. So, this basically shows that in the of the total operational time, let us say a day, what is the loading? If you take a loading of say 40 to 45 or 50 to 50, a particular loading level, for how much does it stay? What percent of the time? So, there are some things which are important to note here. Firstly, note that the fan size must be selected based on the 100% consideration. So, because the fan, for however small time the 100% demand comes, if you select the equipment such that that demand will be met, then the fan size will be selected by the 100%, but most of the time it will not operate at that level. So, rather it will operate most of the time at half level, and it will also operate at very low levels for a very small amount of time. So, this is a typical load characteristic. Now, let us see what happens. So, we need to shift this operating point, right, all the time. So, let us see now what happens if we shift the operating points. So, this is summarized. So, it says that this is like roughly, suppose, because we are going to see an example. So, suppose in our example 100% CFM means again basically flow, cubic feet per minute, this is CFM means Q. So, 100% flow stays for 10% of the time, 80% flow stays for 40% of the time, 60% for 40% of the time, and 40% 10% of the time. Imagine such a case, okay. Then now let us see that what are the various ways of controlling. One of the easiest way of controlling a airflow is to switch on and switch off a fan. This happens regularly. If you see a home air conditioner, you must have noticed that the fan, in that case the compressor switches on and off, right. So, it is a kind of on-off control. So, in a similar way, if you want to control flow, then you can also switch on the fan. So, what will happen if you do that? So, you see, if you switch on the fan, suppose the flow rate will rise for a little time, then it will fall again, and then you will switch it on and then switch it off. So, you will be able to establish an average flow, and this average will actually depend on what is known as the duty ratio. So, this is on, this is off. So, basically the average value will be or rather actually what will happen is that if you it will not rise slowly, because the time constant will be fast enough, rather it will be like this. So, for the moment you switch it on, some flow will be established, the moment you switch it off, that flow will fall. This is an approximation, actually the flow will rise fast and it will fall fast. So, if you approximate it as a square wave. So, again if you switch it on and switch it off. So, basically if this is the flow rate Q max, then the average flow rate will be given by Q max into T on by T on plus T off. This is very easy to know. This is T on and this is T off. So, the average flow you can change by simply increasing T on, by simply changing T on and T off. Okay. This is probably the simplest way. You need nothing. You only need the motor and the fan you anyway need, but as far as equipment for driving the motor is concerned, you need nothing. You just need to switch on the motor and switch off the motor at a certain frequency or a certain rate. For that also you need some equipment, but that is very simple. But this is hardly ever used because of the fact that there will be flow pulsations, and these kind of fans are typically used for industrial processes. We use them for cooling, for things like combustion. So, what will happen in the furnace, for some time suddenly lot of air will come. So, when a lot of air will come, if there is, see, what we want to do is we want to have, we are giving fuel and we are giving air. So, to get the maximum thermal efficiency from the fuel, we need to have a fuel air ratio, perfect fuel air ratio, such that full combustion of the fuel will take place. So, if you put more air, then also air is wasted, and if you put less air, then the fuel will not burn. So, in other words, that pulsating value of flow is not good for combustion flow control. So, similarly, another major application for flow control is for cooling. So, it is not good to, so if you sometimes if you send coolant and sometimes if you do not send it, then the temperature on the equipment will be pulsating, and this temperature may affect reaction rates, it may cause thermal stress on the equipment. So, in general, for industrial flow control problems, we cannot tolerate such pulsations. So, therefore, this on-off control method is not good. So, we go for other methods. So, what are the other methods? So, another very simple method is, so on-off control is the simplest of control. There is going to be temperature fluctuation, basically flow fluctuation will may cause temperature fluctuation. Sometimes for home applications it is used when you have less load and you have a large volume. So, if you so there is a lot of thermal capacitance. So, little bit of flow variation will not be felt because of large volumes of room. So, I mean sometimes for home applications, ventilation, HVAC applications, this kind of control is used, but generally not used industrially. The next control which is used is called the outlet damper control for the fan. So outlet damper means, basically a damper means it's like a set of vanes, just like this, sometimes on the you must have seen what are those called? They're when you put something on the windows to keep out the sun. So there you can change gaps. You can move them, either you can keep them like this or you can keep them like this, so that some air can flow. So basically dampers are also similar things. So what you do is you put a damper at the outlet of the fan. So basically the damper puts a resistance and does not allow air to flow clearly. So by that you try to reduce the flow. That is a very, it's a relatively simple method of flow control, because the controls required for creating a particular resistance in the damper or creating a particular damper angle is actually very simple. But what is the third method? The third method, and which is the very energy saving method, is variable speed fan control. So you do not put any damper, but you rather change the speed of the fan and reduce it when you require less flow. But for that you require a variable speed drive of the motor, and that is much more sophisticated technology is required, especially when the motor is large compared to dampers or valves.